This video is on evaluating the Gaussian integral. In this presentation, we seek to evaluate the integral from minus infinity to infinity of e to the minus x squared dx, which corresponds to finding the area under the following curve depicted here. It can be shown that no antiderivative for e to the minus x squared exists in closed form, but we can be assured that the improper integral converges by the comparison test for improper integrals. In fact, it was Carl Friedrich Gauss who first did this calculation explicitly in 1809. In evaluating the integral, we will use a clever trick due to him. This integral is of interest because it has many far-reaching implications in diverse fields, including statistics, physics, and engineering. Let's begin by defining the integral of interest to be equal to I. So we have that I equals the integral from minus infinity to infinity of e to the minus x squared dx. Now we can make an important observation here. Notice that even if we change the variable x appearing in the integrand to be the variable y, both integrals e to the minus x squared and e to the minus y squared from minus infinity to infinity are numerically the same because they converge to the same number by the comparison test for improper integrals. Now is the part where Gauss comes in. Notice that if we take I squared, aka multiplying the two integrals together, then we can use Fubini's theorem to convert them both separate integrals into one double integral, because both integrands are functions of a single variable, so we can combine them together into a double integral of a function of two variables. So now we're interested in integrating e to the minus x squared plus y squared dx dy. This might seem like we're making the integral more complicated, but this will actually help us out in the long run. So here's the integral we want to evaluate. Now looking at the integrand, this factor of x squared plus y squared almost begs us to use polar coordinates. So if we convert this double integral to polar coordinates, then we get that x squared plus y squared equals r squared, and that dx dy becomes r dr d theta via the Jacobian transformation rule. All that's left is to change the bounds on the integral, and because we're integrating over an infinite square in the Cartesian plane, in polar coordinates that corresponds to integrating over an infinite circle. So that means that theta ranges from 0 to 2 pi, and r ranges from 0 to infinity. And now we can use Fubini's theorem again, because both the integrands feature functions of only a single variable. So we can split this double integral into two single integrals, one of r times e to the minus r squared dr from 0 to infinity, times the integral of d theta from 0 to 2 pi. And if we look at the first integral, we see that we can use a u-substitution to evaluate it. If we make the u-substitution u equals minus r squared, that means that du is minus 2r dr, which means the integrand turns into minus 1/2 e to the u du. And we still have to change the limits of integration, and those become 0 and minus infinity accordingly. And the second integral is actually really easy, because it's just the integral of 0 to 2 pi d theta, which is just 2 pi. So now all we're left to do is integrate minus 1/2 e to the u, which is again minus 1/2 e to the u, and evaluate from 0 to negative infinity, and then multiply by 2 pi. So evaluating the integrand from 0 to minus infinity, we see that e to the minus infinity converges to 0, and e to the 0 is 1, which means we're simply left with minus 1/2 times negative 2 pi, which is just pi. And since I squared equals pi, that means that I equals the square root of pi. But what is I? I is just the original integral we started with. So we've been able to determine that the integral from minus infinity to infinity of e to the minus x squared dx is equal to the square root of pi, which is kind of a strange answer because just looking at it, you wouldn't really expect pi or the square root of pi to show up anywhere, but it does. And generically, if we were to repeat this calculation again with some arbitrary parameter values a and b, we would see that the profile of a general Gaussian function is e to the minus a times x plus b squared. If we integrate that from minus infinity to infinity, we get the square root of pi over a. So this is sort of a generalization of the result we just derived for the a equals 1 and b equals 0 case. And that completes our evaluation of the Gaussian integral.